Okay, so here we are. Example questions, kinematics. This is from page 56 in the textbook. Okay, so here we go. Just a reminder of the formulas that we're going to be using is up there. Let's look at example number 7. Kitty O'Neill, a female dragster, reached a speed of 628 kilometers an hour from rest in 3.72 seconds. How far did she travel in that time? So we are looking for the letter D. We're looking for D. That's fast, isn't it? Now, would that be the initial, average, or final velocity at? That'd be the final, right? 6.28, that would be the final. What would be the initial? 0. So we're going from 0 to the final of that. We've got our time. What distance or what formula am I going to use? D equals V over T? I can't use anything with an A in it, can I? In fact, is this a two-step formula? Let me just see here. What have I got? I got VI, I got VF, and I've got T. The only ones that have distance in them have an A in them, right?
Where is the second one?
This one here? I could use that one there, but I don't have V bar, do I? How do I get V bar? Okay, we could do that. Sure. Okay. Now, do I need to change that 628 into meters per second, you think? Because this is in kilometers per hour. This is in seconds, so one of them is going to have to be in seconds, right? So step number 1 is going to be 628 divided by 3.6. Okay, so that gives me 174.4 meters per second. Now, if I'm solving for the average velocity, don't you think I should just solve for acceleration and use one of the new ones? No?
No.
Okay.
Let's do it the easiest way.
Okay. So that's going to be 174.4 divided by 2. I'm going to have to recalculate this. Although I should be able to divide that by 2 in my head. 87.2.
Very good.
V bar equals D over T. 87.2 D over 3.72 seconds. 324 meters. Let's go to example number 8. Example number 8 is pretty easy too, I think. This one has a Ferrari moving at 20 kilometers an hour and accelerates to 230 kilometers an hour in 7.5 seconds. As it does so, it covers an unknown distance. Find the distance covered. Now, you guys, I'm going to insist on doing it the other way, just to show you.
Do it real slow.
Am I going too fast for you, Mary?
Well, apparently I'm like the slowest writer in the world.
Oh.
You are?
You should sharpen your pencil.
Sharpen your pencil.
No, my pencil sharp.
Yeah. Okay. Well, first step is I'm going to have to take my speeds and convert them to meters per second.
Why do we have to do this every time?
Because that's the way the question gave to
Why
us.
don't we just make it a little bit simpler?
Oh, bellyache, bellyache.
I don't know what that means.
Means quit your complaining.
Not clear.
Okay, so convert them to meters per second. All right, now that I've converted them to meters per second, I'm going to find the acceleration by going A equals delta V over delta T. The change in velocity is going to be, I'm going to write it like this. Did you start writing that already? I'm going to write VF equals VI plus AT. Sorry. It's the same formula, really. Final velocity is 63.9 is equal to 5.6 plus A times 7.5, giving us A is equal to 63.9 minus 5.6 all over 7.5, giving us an acceleration of 7.77 meters per second squared. No, 5.6, Mary. This number right here. Right? 5.6. See the 5.6 right there? Same number. Which one should we use now? D equals VIT plus a half AT squared?
Yeah.
I got A, I got T. Sure, we could use that one.
All right.
So that's going to be now 5.6 times my time of 7.5 plus 1/2 of 7.77 times the T value, and make sure you square it. Exactly.
I should see pre-calc 40 then.
Just you wait. 888. Oh no, hang on, wrong number, wrong formula. Wrong answer. 260.8.
What?
200. That's the answer. 260.8. That's what I got.
Well,
All right. So looking at number 10 here, yes, the 30 milliseconds.
Ooh, did you just 7.7? Did you? Never mind.
Okay.
0.3 off. but it's-
30 milliseconds. You have to convert that to seconds. So millisecond, milli means thousand, right? So it's just 30 divided by 1,000, or 0.03 seconds. The distance is 40 centimeters, which is 0.4 meters, right? 0.4? So now to find the acceleration, which one has D, A, and T in it? Yeah, this one right here. I need a formula that has distance in it. And now, what is the initial velocity of the airbag? Now, does it matter that the car is traveling, say, 60, 70 kilometers an hour?
no. 'Cause
Here-
it is a certain- it's only
Deploys it.
Yeah, it's its own reference system, right? It's traveling 0 relative to a person sitting in front of it. You're right, Quinn. Good way of putting it.
So we can just get rid of that whole percent.
So it's going to be 0.4 equals, that part just sort of disappears. And you get 1/2 of A times 0.03 squared. Right? So now some algebra skills here, right? Get rid of the half by taking to the other side and multiplying by 2. So that's going to be 2 times 0.4 all over 0.03 squared.
So
Now,
you get rid of the VI and T
because the initial velocity is 0. The initial velocity of the airbag is 0.
How do we get rid of the half?
Well, it's like a divide by 2, right? Like times by a half is like a divide by 2. So to get rid of it, it ends up becoming a multiply by 2.
Did you get? I had a stupid number.
When you say stupid, do you mean 888.9?
Well, I mean, 2,666.
divided by 0.0.
It should be 888.9.
You do the 0.03 squared.
Yeah, it's got.
I did it second.
If you do it on your calculator, if you go 2 divided by 0.4, sorry, 2 times 0.4 divided by 0.03 squared equals, you should get that number. You got to make sure you go equals.
I did hit equal, but you were.
Those are all relatively easy. Now,
Oh,
I'm going to do a couple more here, then 2 more. Number 11 is Jane Bond, James's lesser-known cousin.
Was it 2222?
Jane.
The answer on the last one was
I need a school.
88.9. Jane Bond runs down the sidewalk, accelerating uniformly at a rate of 0.2 from her initial velocity of 3 meters per second. How long will it take Jane to travel the distance of 12 meters?
First name. Hello.
So this one's a little bit more challenging. This one, the acceleration here is 0.2. Her initial velocity is 3, and we know that the distance traveled is 12. So which one has D, VI, A, and we're looking for time?
The half one.
The half one.
Half one. We use a half whole like every single time.
We use it a lot, yeah. It's a popular formula.
I almost never remember
E
that.
equals BX.
Plus 1/2 AT squared. Okay, so it's going to be 12. Now what's the initial velocity? Now in this case here, unlike the one with the airbag, there is an initial velocity. So it's going to be 3t plus 1/2 of 0.2 t squared. Now, what happens when you've got a t and a t squared? You curse me, because now we're going to have to do what? Quadratic formula.
Dirt. Let's just erase that.
So I'm going to take everything to the right-hand side.
Kind of question.
Yes.
Can you not use that formula and not do it? Like, if you use the other one, you would go okay, though.
Because the question is how long, so I have to use time.
Yeah, but is there why you put that t squared? Ah! What was the first one? E equals VI plus VI plus AT theta t. Delta t. What
A
do
equals delta V over T, so you can't use that
I
one.
have to do this one? That's stupid.
So when you do the quadratic formula, you need to set one side equal to 0, Mary.
Which side?
When you, doesn't matter.
Oh,
Set one side equal to 0. Now, most of the time you want your t squared value to be positive. Okay? You want your t squared value to be positive. So in this case here, this is already positive, so I'm going to take everything to the right-hand side. So I'm going to write a 0 on the left. 0 equals.
do you want to put in that order now?
Now, it's traditionally, yes, you want to put it in the ax squared plus bx plus c order. So I'm going to write that as 1/2 of 0.2 or 0.1 t squared
So you're just doing that
5.1
calculation.
plus 3t,
5.1 over half.
because it's half of 0.2, and then it's going to be minus 12. All right. You know, oh yeah, you guys don't. Okay, so we're going to go x equals. Now, is it x equals? In this case, it's really t, right?
T equals.
T equals, it's minus b plus or minus the square root of b squared minus 4ac all over 2a. So in this particular case, that's going to be minus b, that's going to be minus 3. Remember, the b is this one. Plus or minus the square root of b squared, which is going to be 3 squared minus 4 times a is 0.1 times c, which is minus 12, and it's all over 4ac. All over 2a, which is 2 times 0.1.
What's your the 4 negative 1?
The 0.1, right? The a is 0.1.
Oh, minus.
I need more ruler.
Wait, what's C?
What'd you thought?
C is minus 12.
B 4.
Oh,
4ac, George.
yeah.
This isn't even getting close yet. Yes, it does. You don't know how to use it? Well, I'm showing you right now. Okay, so now we got to do some, we're going to go minus 3 plus or minus. Now, inside the square root, right, I've got 3 squared is 9, right? Can I do that all in one step kind of thing? I got 3 squared is 9 minus 4 times 0.1. Doesn't matter. Times minus 12. And you should get, I get 13.8.
Is our answer?
You need the square root of 13.8,
Yeah.
which I'm now going to square root.
So T equals square root of 13.
No. So I get plus or minus 3.7 all over 2 times 0.1, which is 0.2. So it's minus 3 plus or minus 3.7 all over 0.2. Now, the quadratic formula is going to give you two answers. One might be positive, one might be negative, or you might get two positives, right? But one way or the other, my time has to be positive.
Obviously, you can't have.
You can't have negative time. That's right, Zach. So do you have to do both the plus and the minus?
Yes.
No. In this case, I've got minus 3. If I do the subtract 3.7, I'm going to get minus 6.7 divided by a positive number is going to give me a negative. So do I even need to do the subtraction one?
No.
No. You only need to do the the add one, right? So it's minus 3 plus 3.7, which is just 0.7 over 0.2, or 3.5 seconds, which seems about right. 3.5 seconds. If you did do the subtract, you would get minus 33.5, which clearly doesn't exist. Okay? That's technically what her speed would be in the opposite direction if she decelerated, if she was going backwards. Okay, now, this next one actually is hard. This next one is hard.
You know, with the 2.5,
No, yeah.
Now, I clearly need more room than what's here.
you get 13.7.
You guys have a new page, I think, right?
No,
Almost. You're gonna have to squeeze here.
you're squeezing it.
You're gonna have to squeeze. Yeah, I'll have to clean this up and give you a whole new page. If you want, you know what? If you want, you might want to do Fred and Barney on the backside, like where it's blank. You might want to do Fred and Barney on the backside where it's blank.
Is it really long?
It's long, yeah. I need to give you more space. Okay. So Fred and Barney are at opposite ends of a 1 kilometer long drag strip, and they're matching race cars.
9 minus whatever. This is
Fred and Barney are at opposite ends of a 1 kilometer long drag strip, and they're matching race cars. Fred accelerates from rest toward Barney at a constant 2 meters per second squared. Barney travels toward Fred at a constant 10 meters per second. How much time elapses until they collide? How much time before they run into each other?
They're basically gonna hit each other.
They're basically playing chicken, and they're going to run into each other, right? Okay. So what we've got Fred over here, and we've got Barney over here, right? Does it matter who we put at what end of the track? No, it does not. Okay? So Fred's going to the right, and they're going to have a fiery crash somewhere in the middle. Right? So Fred is moving to the right. His direction is positive. Barney is moving to the left. His direction is negative. Now, when do they collide? Well, they collide when they're at the same place at the same time, right? Okay, that's the fiery crash. You really, Mary? All right. So now, Fred's position is defined by what? Fred's position, P-O-S-N. Well, he starts at 0, right? But his position is equal to his displacement. Right? We're going to start Fred at position 0. Barney, however, starts at position plus 1,000. Why does he start at plus 1,000? He's 1,000 meters away. He's a kilometer away. His initial position is plus 1,000. Fred's initial position is 0. So his position is actually his displacement, Fred's displacement. Now, Fred is moving. He's accelerating, right? Okay. So which of the formula has accelerations in it? Well, dF, displacement Fred, is equal to VIT plus 1/2 AT squared. His initial velocity is 0. So we have 1/2 of A, 1/2 of 2. Do we have the time? No, in fact, that's what we're solving for. How much time elapses until they collide? The problem is also, I don't know how far he travels. I can't solve that.
So why do you do it?
Oh, let me show you. I'm going to reduce this down to dF equals, fortunately it's 1/2 of 2, so it's just Fred's position is his displacement, which is equal to t squared. Right? Like if he travels for 3 seconds, he's going to go 9 meters. Right? 4 seconds, 16 meters, and so on. Okay, over to the Barney side of it, things. Barney's position is not equal to his displacement. His initial value is, in fact, 1,000. his position is 1,000, and he's moving left, so it's actually 1,000 minus dB. His position is 1,000 minus his displacement, right? If he moves forward 10 meters, his position is 990. If he moves 100 meters, his position is 900, and so on. Okay, so Barney's position is equal to 1,000. Now he's traveling at a constant speed, is he not? He's moving at a constant 10 meters per second. So his displacement is actually equal to V bar T minus. This is equals. Barney's position is 1,000 minus VT. Or Barney's speed is, I think it's 10, isn't it? Okay, so Fred's position is T squared. Barney's position is 1,000 minus T squared. When do they smack into each other? When their positions are the same. In other words, when this equals that. Okay, this is a system of equations. It's two. You've got two equations here. You've got df equals vit plus a half at squared, or sorry, really you've got df equals half of 2t squared, and here I've got the same displacement, the same position is 1,000 minus vt. So these two things are equal to each other. So in other words, t squared equals 1,000 minus t squared. Right? It's like system of equations, and I've
Yeah.
oh 10t. Sorry. Yeah, 1,000 minus 10t. It's like a system of equations where I've substituted for one, or I've isolated for one, and then I've substituted in the other. So now I've got an equation with just t's in it. Regrettably, it's a t squared.
Direction of
Okay, move everything over keep per one.
Okay, so we're going to move it to the left, right? T squared we want to be positive, so it's going to be t squared plus 10t minus 1,000 equals 0. Now quadratic formula. X equals minus b. No, you can't factor the t out. You can, it's not going to get you anywhere. Minus b plus or minus square root b squared minus 4ac all over 2a. I'm going to pause and let you guys try the quadratic formula on your own. Okay, so you should have x, or t, I guess, really, is minus 10 plus or minus 10 squared minus 4 times 1 times minus 1,000 all over 2 times 1. And you should get either 27 or minus 3.7. Is that what you got?
Yeah.
27 or minus 37 seconds? It can't be minus 37. That doesn't really exist. See, it's not hard. So it's 27 seconds. After 27 seconds, they'll be in the same position, right?
And they will explode.
Into a fiery crash.
So negative 10 plus 6.
You know what? It would be a real good idea if you gave, example number 13 is almost identical. Jack is running at 6 meters per second to catch a bus. He sees it start to move when he's 20 meters away. If the bus accelerates at 1 meter per second squared, will Jack overtake it? In other words, will he catch the bus? And if so, how long will it take him? So this is the same thing, except that
They're both going the same way.
Fred and Barney are going towards each other. This time, they're both going same way. So the question is, will Jack catch the bus? In other words, will Jack and the bus ever be in the same position at the same time? So exactly the same time. I will tell you an interesting little story. My nephew, for whatever reason, right? Jack's position is equal to his displacement, which is v bar times t, or 6t. The bus position is equal to its displacement plus 20, because it's starting at a plus 20, right? Jack is here at 0. The bus is at plus 20. So I go, yeah, vi, the bus's initial velocity is 0, so that's 0. I got 1/2 of 1 t squared plus 20, or 0.5 t squared plus 20. you probably want the t squared to be positive, so I'm going to write 0.5 t squared plus 20. This 6t is going to go to the, whoa. Like I set these two equal to each other, right? So in fact, this is going to be a minus 6t in there, right? Equals 0. Does that make sense? Does that make sense, Mary? Why is it negative? Because this 6t is going to go to the other side of the equals,
Oh,
right? To line up with these guys. So now it's just a simple matter of solving quadratic formula there. Well, maybe simple. So when you do the quadratic formula, you get t equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Please notice that I'm writing that out every time, even though I know it already. So it's going to be 6 plus or minus 6 squared minus 4 times 0.5 times 20 all over 2 times 0.5. 6 plus or minus the square root of, you got 36 minus 4 times a half is 2 times 20 is 36 minus 40 right in there, right? 36 minus 40 all over 1. So what does it mean when there's no time that they're in the same position? It means Jack does not catch the bus. And if you actually stopped and you looked at it, you would realize there's no way he's catching this bus. Okay? If you look at the numbers, right? He's 20 meters away. He's running at 6 meters per second, right? So for him to cover that 20 meters, it's going to take at least, if he's running at 6 meters per second, just for him to get to the bus itself, if the bus wasn't moving, it would take him more than 3 seconds to get there, right? 3 1/3, you're right. But the bus is already moving, right? After 1 second, the bus is accelerating 1 meter per second. It's only going to be half a meter. Okay, that's no big deal, right? But in that next second, it's going to go even farther and farther. The chance, you should be able to tell just from the numbers that the chance of him catching that bus are pretty slim. He is close.
Unless he's used some ball.
He is close.
Yeah, you got to pass just 6.
No, that would be faster 6 meters per second. He is close. In fact, I think if you get, well, how do we know? How do you know how close it is? Yeah, it's only -4, right? Square root of -4 is 2i. Like if it was plus, it'd be 2, right? So he's pretty darn close, but not close. Okay. I threw that in there because I want you to realize what happens when you can't do it. It means that they're never at the same position at the same time. Okay. There's a whole whack of questions in the book that you can now do. I'm going to pop that video in right away. I'll just give you a couple for today.
I was going to say here,
Page 64, numbers 1 to 3, and I've got a few more that I'm going to show you tomorrow.